Today we're gonna spend one more hour talking about maximum and minimum problems. Just the basic one. We are not going to do the applications problem. We just learn how to figure out the local max and local min for the function of two variables, and then we're gonna take a look at your homework number 4 that I just posted a few minutes ago. So let's try to do the section 12.8 in the book first, maximum and minimum problems. So this is continuing from last week. So last week we stopped at the chain rule and partial derivative here with the tedious calculations. But this week we're gonna start from page 27, which is maximum and minimum problems. So the thing that you learn in calculus 1 is that you learn that when you have a function fx. So let me give you a quick review from calculus 1. So in calculus 1 you have the function fx, and when you want to find maximum or minimum, you can just start from taking the derivative, right? You take f prime x and then you set it equal to 0. Everyone should remember how to do this, and then you solve for this equation. Once you solve for this equation, so you're gonna get the x value that give you the equation f prime x equal to 0. That x gonna call the critical value, right? And then once you get the critical value, you do the second derivative test to check if it is a maximum or minimum. So we're gonna do the same thing here in 2 dimension. This is in 1 dimension. So in 2 dimension, you're gonna have function f as well. And then now you're gonna take derivative. But when you take derivative, you're gonna take with respect to x and with respect to y. And then you're gonna have 2 equations. It's gonna be a system of equations. And then after that, you solve for x and y. That x and y are gonna be your critical points. And then once you have your critical points, you can plug into the function and use second derivative test to show that it's actually maximum or minimum. So first of all, this is a definition of local max and local min from the book. You know that a function f has a local maximum if fxy less than or equal to fab for all xy in the domain of f in some open disk center at AB. What it means is that when you want to say that it is actually a local max, it is actually this point, local max. So all you need is you need that in the neighborhood of this point. So you're gonna need fxy to be less than fab. So AB gonna call local max when its neighborhood less than or equal to AB. This is actually the definition of local max, which similar to, you know, match with your instinct, because this means the max. The min should be the one that when you take a look at this point, so you're gonna see that in its neighborhood, it's gonna be all the point that is at least greater than or equal to them. So that it's going to be the local minimum. So what we're gonna do is we're gonna learn how to find the local max and local min when the function is given. So we are not going to draw the graph, but we're gonna just look at the equation and see where it's maximum and where it's minimum. Okay. So this is the first thing that you're gonna learn from this chapter. Theorem 12.13, derivative and local max and local min value. You know that if f has a local maximum or local minimum, then the partial derivative of f both way with respect to x and with respect to y exists, and they are equal to 0, which means if you know that f has local max or local min at the point AB. Let's say that f has local max or local min at the point AB. It's gonna be the case that f derivative at x, derivative with respect to x at the point AB equal to 0, and derivative with respect to y at the point AB equal to 0. So this is the one property that we know, that if it is actually local max or local min, it must be the case that the derivative, the partial derivative, gonna be 0. So from this idea, so we're gonna call all the points such that the partial derivative equal to 0. We're gonna call it critical points. So the way that we're gonna do is we're gonna do the same thing as we learned in Cal 1. So we're gonna find all critical points first. So critical points are the point that the partial derivative equal to 0. And then once you get the critical point, you just do the second derivative test to check again if it is local max or min. So this is a proof. We don't have to do it now. So this is from the book. That I mean, if you can read it, that's fine. The proof is a little bit tedious here, but actually it does come from calculus 1 when you fix one variable to be constant, and then you can cite the thing that you learned in calculus 1. But here, this is the definition of critical point. The important thing for you start here. So you're gonna say that the interior point AB in the domain F, we're gonna call it critical point when the first derivative and the second, the first derivative with respect to x and the first derivative with respect to y equal to 0, and at least or one partial derivative, at least one of the partial derivative does not exist. So there are gonna be two cases. So if the derivative, the first derivative equal to 0, or if it does not exist, so you're gonna call it critical point. Pretty simple like that. So let's start from taking a look at this example. So this is the example from the book. We wanna find the critical point of x times y, x minus 2 and y plus 3. So what you have to do is you're gonna start from this function, and then you take derivative. Everyone taking a look at this one. So we're gonna take derivative of f with respect to x, and then we're gonna take derivative with respect to y. So the way that you take derivative, so you get this part. So how would you take derivative again? So let's see, if you have f prime x, right? F subscript x, the derivative with respect to x. So you're gonna keep y constant. So it means you pull out y minus y plus 3, right? So this is going to be your constant. So you pull out, and then you have derivative with respect to x of x y times x minus 2, right? So you just pull out y minus y plus 3 first, because that is constant, and then now you take derivative of the thing inside here. The best way to do it is just you multiply first. Do not use the product rule because it's gonna be a little bit confusing. So you can like, actually you can pull out one more y if you want to. You can pull out y here. If you don't want y, you can pull out y, and then you're gonna have x squared minus 2x, which you're gonna differentiate. So you get 2x plus 2 here, and then that means you have y times y plus 3 and then times 2x plus 2, which is this one, right? And then you're gonna do the same thing with this function. Take derivative with respect to y, and then you get this. Okay, and then the same thing in calculus 1. Once you get the derivatives, you set it equal to 0. But now you can see that you have two equations. So it's gonna be a system of equation. A system of equations. So you need to solve for this system of equation. How do you solve it? So the people have a hard time to solve this one, but usually when you have system of equations, you're gonna solve for x and y by trying to get rid of one variable first, and then make one variable to be the same, and then you add them up or you cancel them. So you're gonna have solution of x and y. Here what we're gonna do is we're gonna start from this equation, and then we're gonna say that the first equation is satisfied if and only if y equal to 0, x equal to 1, and y equal to negative 3. So we start from the first equation here. Oh, okay. This y, right, okay, pull out y, okay. And then this equation, everyone, you're gonna just solve for root of this equation. So it's gonna be y equal to 0, x equal to 1, and y equal to -3, right? So you solve, and solve. So once you get y equal to 0, so you say that when y equal to 0, then you plug in y equal to 0 to the second equation. So you get 3x times x minus 2 equal to 0, right? Because once you get y equal to 0, this is the solution from the first equation. So you plug in here. So this is going to be x times x minus 2 times 3, which is this one. And then you solve for x equal to 0 and x equal to 2 here. So which means you have two critical points from the first equation here, 0, 0, and 2, 0. So the next one is you substitute x equal to 1. Because this is the second solution from the first equation. So when you have x equal to 1, you plug in here 1, 1. So you're gonna get negative 2y plus 3 equal to 0. And then you solve for y, so you get 1 and minus 3 over 2 here. This is another critical point. And then the last one, y equal to -3. So it come from here. And then once you have y equal to -3, you plug in back here. So you're gonna get this equation. And then the roots gonna be 2 and 0. So you get 2 more critical points. So at the end, you get 5 critical points. And this is going to be all candidates for local max and min. So basically the idea gonna be the same as calculus 1, but it's just getting more complicated because you have 2 dimensions. So if you don't know how to solve the system of equation, you're gonna be in trouble because it's like you need to solve for x and y at the same time. We're gonna have more example for you to practice today on the last 2 examples. But this is the big picture when you find the critical point. Sounds good? Alright, so now we're gonna take a look. Once you have the critical points, how do you know that it's gonna be max or min? So the second derivative test, in one dimension, you used to take derivative one more time, right? And then you say that if you take the second derivative, if it is less than 0, you're gonna say that it is max. If it is greater than 0, you say that it is min. This is what you do in 2 dimensions. Take a look at theorem 12.14 here. The second derivative test to check that the critical point is max or min. So this is what you're gonna do. So you're gonna compute a term called d, which is you differentiate with respect to x 2 times, differentiate with respect to y 2 times, and then you minus fxy square. Once you compute this term d, you take a look at d greater than 0 or not when you plug in a, b inside there, or d less than 0 or d equal to 0. If d is equal to 0, it means the second derivative test is inconclusive. So you don't know anything about that point. But if your d here less than 0, it's gonna call the saddle point. We're gonna define it later what it is. If d greater than 0, you take a look at fxx. If fxx less than 0, it's gonna be local max. If it is greater than 0, it's gonna be local min. So case number 1 and case number 2, this is what are you looking for. So local max and min. So it's gonna be this max or this min when your d here, sometimes we call it discriminant. So d here gonna be bigger than 0. And the sign of the derivative fxx here gonna be your decision, it's max or min. But if d less than 0, it's gonna call the saddle point. Saddle point, this is the point that it is the point that similar to the point like the saddle from the horse. So it's gonna be neither max or nor min. So it's gonna be something like this. So you have something that this is a point called the saddle point. So it is not maximum and also not minimum, because it can be maximum and cannot be max and min at the same time, because in one line it is actually minimum. Another line is gonna be the maximum. So it's gonna be like, this is a point that called the saddle point. So the saddle point is the one that you have d less than 0. So once you get the critical point, we're gonna compute your d here, and then you look at the value of d first, greater than 0 or less than 0. So less than 0 means you get saddle point, bigger than 0 it means it is going to be max or min. D here, sometimes called discriminant. The reason why we call it discriminant because you can view this thing as a metric. So this is called the Hessian metric in calculus. So if you put fxx here, fyy here, fxy and fyx here, so you're gonna form the 2 by 2 matrix. And then if you compute the determinant of this metric, so it's gonna be like, you can, I mean like, it is not something like determinant, but it's similar to determinant. Because determinant, actually when you learn determinant, you have to divide it by AD minus BC, whatever. But what are you trying to do here is you're trying to do the cross multiply, fxx multiply fyy. It's gonna be here, the first term. And then you cross multiply here, which you're gonna get fxy and fyx, which they are the same when the function is continuous. So you can square it. And then once you, if you memorize this matrix, so, and then you remember that it's going to be cross here minus cross here, it's going to be your d. And once you get your d here, so you compare it with 0, and then greater than 0 mean you get max or min, less than 0 mean you get saddle point, equal 0 mean you get inconclusive test. So we're gonna just show you by the example, but this is actually the way we're gonna do for checking max or min in 2 dimension. Okay. So it may a little bit, now it's probably a little bit confusing at first how to use it, but let's take a look at example. So we're gonna show this picture. This is a function y square minus x square. We're gonna show that this point, it is actually the saddle point. Okay. Okay, let's do example in the book first. I want to use the second derivative test to classify the critical points of this function. Okay, so taking a look at the function here, if you use the computer to graph it, so it's gonna be the paraboloid here, the shape of here. But let's say that you don't have the computer, so you don't know how to graph it. So you want to take a look at this function, just this function, and tell how do you find max and min for this function. So first of all, you're gonna take the first derivative with respect to x here. So everyone know how to take derivative, right? So you get 2x minus 4. Because differentiate this, you get 2x. Differentiate this, you get 4. Something else, anything else, you get 0 because constant. Differentiate with respect to y. So you have this and this, so you get 4y plus 4. This is constant, this is constant, this is constant, so it's gonna be all gone. And then now you solve this equation, this system of equation. Technically, you have to solve this thing first for the critical point. So you solve to x minus 4 equal to 0, and then you solve for y plus 4 equal to 0 at the same time. So you're gonna get x equal to 2, y equal to negative 1. So this is actually your critical point. Does it make sense? So once you get your critical point, you want to know if the critical point is actually max or min. So this is actually the critical point. This is how to find the critical point. So you can find the critical point by solving these two equations together. So you get the critical point. And then now for the Hessian metric, we just do this fxx, fyy, fxy, fyx, and then now what you're gonna do is you need to take derivative with respect to x one more time. Here you get 2. You take derivative with respect to y one more time. Here you get 4. and then fxy and fyx you can do only one, because you can start from here, differentiate with respect to y, you get 0, or you can start from here, differentiate with respect to x, you get 0. So it's actually you put 2 here, 4 here, 0 here, 0 here, and then the Hessian metric gonna tell you that your d here is gonna be 8, right? So once you get 2, 0, 0, 4 here, you do the cross multiply 8 here, minus 0, so it means your d, it's actually 8 minus 0, which is greater than 0. So once you get greater than 0, you compare to this one. So now it's going to be this case. So you have to take a look at this one. It's going to be max or min. But now, because this question you have fxx equal to 2, less than 0. So it's actually bigger than 0, sorry. Bigger than 0 is actually local min. Does it make sense? So it's gonna be local min here. Yeah. So which match with the picture here, if you put it in a computer, it's gonna be local min. Okay. All right. So this question is like a piece of cake for you, I guess, for the exam. Like final exam, gonna be one question on this one, 7 points.
You should like this now.
The function that I will give on the exam gonna be similar to this one. So we're gonna practice these two examples here. So it's not that bad. So you can trying to do example together. But well, before we do example together on the blank question over there. So this is the one that we did before. This is the function that we already find critical point from the previous question. You can see that when you have more than one critical point, you're gonna do the same thing. So you compute fx, fy, you compute fxx, fxy, fyy, and then you put it in the metric d, right? So d gonna be fxx, fyy, fxy, fyx, and then let's suppose that you wanna compute at the point 0, 0. So what you do is you plug in the value at 0, 0, and then you compute your d. You can see that, and once you get the negative number for d here, it's gonna be the saddle point. 2, 0 here, you plug in, you get negative 36 saddle point. So here you plug in, you get 9. So it's gonna be local max because fxx less than 0 as well. So you keep doing it. If you have more than one critical point, you have to do all of them. Okay, so we should do the example now about how to find the critical point. This is the one that they show you in the book how to do it. Okay, let's start from the example 31 together. So y square minus x square. If you put it in the Google, this is the picture of y square minus x square. So let's see. We have fxy, everyone, equal to y square minus x square. So you take the first derivative with respect to x. So you're gonna get minus 2x. You take the first derivative with respect to y. So you're gonna get 2y. So to find the critical point, so you need to set fx equal to 0 and fy equal to 0. So you set both of them equal to 0 and then you solve. So it's gonna be minus 2x equal to 0 and 2y equal to 0. You solve for this equation. Solving this equation yields. So you solve this at the same time, you get xy equal to 0, 0, right? Because this gonna give you x equal to 0 and y equal to 0. So which means this is actually your critical point. You can say now this is your critical point. And then now if you want to know if this is actually local max or min or saddle point, so you compute fxx one more time, so you get negative 2. fyy, you compute it, you get 2. fxy, this is actually 0, or the same thing if fyx equal to 0. Right, and then you put it in the metric d, which is going to be negative 2, 2, 0, 0. So this is gonna be the case that your d gonna be minus 4, which is less than 0. This is the metric. that help you. So your d gonna be actually minus 4 equal to 0, which means 0, 0 is a saddle point. Because it's d is less than 0. So if d bigger than 0, it's gonna be the case that you get max or min. Here, this is the point 0, 0. It is actually the saddle point because on this scale it can be minimum. On this scale it can be maximum. This is the case that we found a saddle point here. Alright, but you know this function is way too easy, right? Because you only have one critical point. Not challenge at all. So we're gonna take a look at when the function has more than one critical point, and that will be more challenge for you to find local max and min. But we're not going to go that far to, you know, the sine, cosine, tangent, or exponential function. We're gonna do polynomials for the class. Okay, so we have two examples here. Example 32. Can you find all critical points for this function and then classify them as a max, min, or saddle points? Okay, let's do it. Differentiate with respect to x. So you get minus 2. This is actually easy one, both of them. But I mean, like, not that hard. But let's see. Negative 2 plus 2x. Okay. This is actually the first derivative. And then okay, let's do y first, and then we do the second derivative. Fy here, you're gonna be minus 6 plus 2y. Okay. And then now before you continue your calculation, so you can take the second derivative. This is actually 2. This is actually 2 as well, right? Because you differentiate, and then you can compute fxy here, so you can get 0 as well. This is the same thing with fyx. So you first find the critical point. So you can see clearly that the critical point, when you want to find it, so you need to solve minus 2 plus 2x equal to 0 and minus 6 plus 2y equal to 0. So you solve this, so you get x equal to 1 and y equal to 3, right? So 1 and 3. So which mean 1, 3, this is your critical point. So when you have 1, 3 is your critical point, now you trying to plug into the Hessian metric. Your Hessian metric gonna be 2, 2, 0, 0. Lucky that you don't have x and y inside here, so you can plug in it 1, 3, and then they have nothing to plug in for x and y. So here you're gonna have your d. It's actually minus 4, or 4, sorry, 2 times 2, and then minus 0, 0. So this is actually 4, bigger than 0. So when you have d bigger than 0, it is going to be the case that you get local max or min. But you observe that fxx is actually 2. So this is actually bigger than 0. So it means the critical point 1, 3 is actually a local minimum, right? This is the case that you only have one critical point as well. Easy one. All right. So I'll let you write down for 1 minute, and then we're gonna do example 33. Well, because the theory said that you take a look at the fxx. you can take, you can view fyy as well if you want to, but it's gonna be a little bit different how to figure out local max and min by looking at fyy. So there is a proof in the book that why we need to take a look at fx, but this is the easiest way. So well, to answer why, so you have to take a look at the proof, which I did not prepare for the proof. So I probably should ask a person who is interested in the proof to take a look by yourself, which is fine. Again, one more time, everyone. So this is actually the second derivative test. So here, you take a look at this, and then you're gonna get local max or min. One idea is that we have to check the sign of the second derivative. It actually came from calculus 1, because when you learn calculus 1, you also have the second derivative test. So in calculus 1, if you differentiate 2 times, you get something bigger than 0, you get minimum. If you differentiate 2 times, you get less than 0, you get local maximum, right? So basically we're gonna take a look at this one, because in 2 dimension, the idea is we fix one variable to be constant, and it's gonna come back to 1-dimensional calculus, and then you can take a look at the sign of the second derivative as well. Okay นะครับ we're gonna go to the last example for this handout. So example 33, and then we're gonna take a look at your homework later. Find all critical points of the following function. Classify them as a minima, maxima, and saddle points. So this one is a little bit more complicated, but not that much, because you have x cubed here. So it means when you take derivative, so you're gonna get x squared back. So you have f differentiate x with respect to x, so you get 3x squared. With respect to x, so you get 3y squared, and then minus 15, right? And then differentiate with respect to y, so you're gonna get 6xy, and then plus 6y. All right, so this is actually the first order derivative, the first order partial derivative. And then now you differentiate one more time. Here you're gonna get 6x. Here you're gonna get 6x plus 6, right? And then now you're gonna have fxy, which is you're gonna get 6y. And this is the same thing with fyx. So you compute all derivative already, but you get this one. Okay. Now you need to find critical points. So critical points are the point that you set up the first derivative to be 0. Okay, and then once you set this thing equal to 0, what happens is okay, and then you solve for x and y. How do you solve for x and y here? So first of all, this equation gonna be 6x plus 6 times y equal to 0, right? This equation gonna be x squared plus y squared equal to 5. I'm going too fast. So I simplify the left hand side, 15 to the right hand side. So you get x squared plus y squared equal to 5. Because I divided everything by 3 as well. And then on the right hand side, I put out y here. So the one that is easy to simplify is this one. Because when you have two things product, you get 0. It means it is actually 6x plus 6 equal to 0 or y equal to 0, right? So because this is like a times b equal to 0, it means either a or b must be 0. And then you're gonna do two cases. Case number 1, you set y equal to 0. When y equal to 0, it means x squared plus 0 squared equal to 5. So you're trying to combine this equation and this equation together to solve for the solution. So set y equal to 0 and then plug in back here. So you're gonna get here x equal to plus or minus 5, square root 5, which means you have two critical points for this case. Two critical points for this case are plus or minus square root 5, comma 0. This is the first two critical point for case number 1. Right. Now case number 2. Case number 2, you have 6x plus 6 equal to 0. Now you solve for 6x plus 6 equal to 0. So you have x equal to minus 1. Right, so minus 1. That's correct. And then you plug in minus 1 back to the equation. So you get minus 1 square plus y square equal to 5, right? Because you plug in back. So you have this from this, right? And then you plug in back here. So you need y. So it's gonna be the case that y square equal to 4, right? So y is plus or minus 2. Which means your critical point for this case, it's gonna be the case that you get minus 1 and plus or minus 2. So basically you have 4 critical points. 1, 2, 3, 4. And then we're gonna just figure out the pattern for each critical point. Okay, I'll let you write it down on the note on the paper first. All right, now we're gonna take a look at how to figure out the critical point. So to save your time, you're gonna draw the table. So it's gonna be easier for you that way. So you can draw the table from here. So you can start that. You have the critical point. The first one gonna be square root 5, 0. The second one minus square root 5, 0. The next one gonna be negative 1 and 2. The one gonna be negative 1 and negative 2. You have 4 critical points. So every time when you do 4 critical points here, so you're gonna just compute your D. It is actually here you have 6x plus 6 here, and then you have fxy 6y, this is 6y, right? And then you compute your D, so it's gonna be D, it's actually 6x times 6x plus 6 and then minus, so you do the cross here, minus the cross here, so you get minus 36y squared. Does it make sense? And then now you try to compute your D here, and then this is the classification at the end. So the second column here is gonna take time for you to compute. So your D here gonna be you plug in 5, next square root 5, and 0 here. So once you plug in square root 0 here, so immediately you get 6 times square root 5 times 6 square root 5 plus 6. So it doesn't matter what number is, but you actually know that it's greater than 0. Does it make sense? Here you have D as well. So you plug in 6 times negative square root 5. Here you get 6 times negative square root 5 plus 6. And then minus 0. So is this going to be bigger than 0 or less than 0? You have to think this way. So 6 times negative square root 5. So you can like pull out number 6 if you want to. So you get negative square root 5 plus 1. So here, would you agree that this is actually negative? And then this is also negative, right? So you multiply it together so you get positive. You don't have to compute it like completely, you just need to know the sign. So here, well, but this one, we don't know yet it's gonna be max or min. We have to take a look at fxx later. But let's try to compute this one first. This is actually 6 times minus 1. 6 times minus 1 is negative 6 plus 6. And then minus 36 times 2 square. So when you plug in negative 1 into this function, so negative 1 gonna kill this term to be 0. So this is actually 0, right? It's gonna be 0 minus something positive. So this is less than 0, okay? And then the same thing here, you're gonna get 0 minus, this is actually less than 0 as well. Because you plug in minus 1 on this thing, the one that I highlight in yellow, it's gonna give you 0. So you have 0 over there, and then minus 36 times minus 2 square. So you get minus sign over there. So here, greater than 0, less than 0, less than 0. So for sure, this is saddle point. For sure, this is saddle point. But on the top two here, you take a look at this. So you look at fxx. Fxx is actually 6 times x, right? 6 times x here. So it's gonna be 6 times square root 5. This is 6 times minus square root 5. This is bigger than 0. This is less than 0, okay? So this is actually local minimum, right? This is local max. And then this is at the end of the question. So you actually classify all the critical point already. So negative square root 5, 0, this is local min. Minus 5, 0, this is local max. These 2 points, they are saddle point. Does it make sense? Tedious in calculation, but in concept, not that hard. So you just compute the first derivative, set it equal to 0. Solve for the equation. Once you get your critical point, you plug into D to find the discriminant, and then you compare with 0. So the case is gonna be all greater than 0 or less than 0, because when it is equal to 0, I'm not going to put it on this class because it's way too hard. So you're gonna just get the D that bigger and less than 0. Less than 0 means saddle point, bigger than 0 means max or min, depend on the value of fxx. Well, if you put boundary on the domain, you can find absolute max and min, but that one it's just way too hard to explain, because you need more technique to understand how to find the boundary, how to find the max and min at the boundary. So we're gonna skip that part. So the part that we're gonna do is we're gonna just do local max and min. For absolute max and min, you can actually apply it later if you want to, because you do need the boundary first, and then you can apply the boundary into the condition as well. All right, so we're gonna taking a look at now at the my course view. 1 second. Even some of you still working on it. Good. All right, a lot of things that you have to do this week, next week, and the following week. So let's go back to my course view. Here we go. So if you take a look at my course view now, the thing that you're gonna see first now is if you click on assignment, so you're gonna see there is homework 4 exists now. I just posted this morning. So for homework 4, what you're gonna do is you're gonna complete all the questions and then submit by April 24th, which is this is the April 3rd. 3 weeks from now, you need to submit homework 4. So homework 4 is going to be the one that I asked you to do 8 questions in this PDF file, and then you're gonna submit it on the by PDF file as well. So let's take a look. Oh, so you can take a look at you can go back to the is it the internet is bad, or it just is it because I don't have the internet here? Seriously? Tula Wi-Fi. Okay. So we can just it's actually here homework 4 questions. You can click on it, homework 4 questions. And then you gonna see that the first question is limit. So this is similar to what you're gonna see on the exam as well. So the limit, the thing that you learn for limit is that you learn that for limit you have the technique that you do the factoring or conjugate or picking two lines that you give you different limits, and also you use a squeezing theorem. So this is the question that mix in one question. So question asks you about limit here, and question 2 is 2 and 3. This is the continuous. So if you know how to compute limit now, you can check the continuous at the point. So question 1, 2, 3, they are different. They are similar to the one that we did in the lecture about limits and continuity. Question 4, this is how to take derivative. I give you a function and then practice on taking derivatives. And then question 5, this is a practice on the chain rule. So you draw the diagram and then you do the chain rule. Questions, the last 3 questions, 6, 7, and 8. So question 6 still chain rule. Question 7 still chain rule, but a bit more tedious because you have to do chain rule into the and the second order derivative. So it's question 7 is gonna be a little bit tedious, but question 8, this is the critical point, the thing that you learn today, and then you do the second derivative to check if it is max or min or saddle point. Okay, 8 question here. So you submit it by April 24th. So for 3 weeks from now. Yeah, so that's the first thing that you have to submit, and it's gonna be 20 points, with going to be 15/4. What is that? 3.75 of your grade, of your total grade. 3.75% of your grade. Yeah. Does it make sense? That's homework. And then now taking a look at the schedule now. So the thing that you already done, exam 1, right? Exam 2 you done. So this week on Wednesday you're gonna see the take-home exam for differential equation. So I'll give you 1 week to do it. So submit by Wednesday, April 12. That's the exam 3 for the class. And then homework 4 is already up. Homework 5 coming soon. And then the final exam gonna be the first day, May 8th. That's the first day actually for the final exam. Does it make sense? Taking a look at here, the guideline for the take-home exam here. So the take-home exam gonna be starting from Wednesday here up to this Wednesday up to next Wednesday. They're gonna be 40 points on the take-home exam. We're gonna divide it by 4 and give you 10 points of your total grade. So the expected portion of the exam gonna be separable equations for 12 points. 10 points gonna be homogeneous differential equations, and about 18 points gonna be exact differential equation and integrating factors. So you can do the take-home exam and open the clip at the same time. So I expect that everyone gonna get 40 points, or at least you're gonna get 37 or 38, because this is actually the part that we're gonna help you to get 10 points in the pocket first. So you can calculate yourself that you're gonna get 10 points for the take-home exam. But well, usually when I say take-home, everyone should get like 9.5 or up for the take-home exam. So this is the part that gonna like pull you from the mean to just get a little bit above 80%, so you have more chance to get an A for the final. So this is take-home exam, and for the final here gonna be on May 8th. This one gonna be a little bit harder than midterm, because usually students have a hard time with differentiation and integration more than the differential equations. So this is going to be the one that we test you on limit and continuity, the second derivative test, the partial derivative, the chain rule, the higher order. So you can see that there is one question on critical point and max and min verification. So similar to what we did today, that one is 7 points. And then Wednesday we're gonna start integral, so which is 7 points. That one on the rectangular domain. The part that students usually have a hard time gonna be the polar coordinates, the last one, because you usually need to you used to switch your rectangular coordinate to polar, and sometimes it's like new for you, and then you need more time to digest the material. But that is the final exam. So I expect that final exam gonna be a little bit harder, so your grade could be dropped a little bit. So make sure that you do take home exam and get full credit, so you have 10 points in the pocket first. So because due to the pressure, the final gonna be a little bit tough for you. ใช่สอบก็เราสอบวันที่ 8 เลยไม่ใช่เหรอเราโน้ตไว้ตั้งแต่เปิดเทอมวันที่ 8 ดีแล้วเอาวิชาง่ายขึ้นมาก่อนเดี๋ยวสอบฟิสิกส์ก่อนเดี๋ยวก็ร้องไห้อีกว่าแบบโอ๊ยทำไมเอายากจังเลยอะไรอย่างเงี้ยฟิสิกส์ like on May 9 ฟิสิกส์วันที่ 2 morning ด้วยเหรอชิบหายแล้วหรืออยากเปลี่ยนเป็นเช้าเหรอวันที่ 8 นี้บ่ายอยากได้บ่ายหรือเช้าเข้าวันที่ 8 เดี๋ยวเราจะได้ไปบอกทาง ISE ว่ายังเป็นไปได้ไหมที่จะไม่ใช่ ISE ทางคุณหมวยว่าจะเปลี่ยนเป็นเช้าได้ไหมพี่หมวยไม่แต่ว่าเมย์ 8เราล็อกไว้บ่ายแต่ว่าอยากเปลี่ยนไหม
ถ้าบ่ายแล้วกลับมาอ่านฟิสิกส์ไม่ทันมันจำฟิสิกส์การบ้านไม่ได้แบบไม่มีเวลา
จริงเหรออยากได้8 เช้าแต่8 เช้าเราไม่ว่างแล้วอะ
9เป็นไหมจ๊ะ
ไม่ใช่เอา8นี่คือ8 โมงเช้า
9 ถึงเที่ยง
เราควรจะคนภาษา
สอบวันไหนบ้างอะวันเดี๋ยวในฟิสิกส์วันที่ 9แล้วมีอะไรอีก
เราสอบ
ไม่แต่ไฟนั่นก็เป็นอย่างนี้อยู่แล้วไหมอ่ะเอ้ยไม่ถึงมันก็ต้องสอบติดๆกันอยู่แล้วไหม
บินเขาออกเขาบอกวันที่12อะ
วันศุกร์อะผมแม่งตายเหี้ย
ก็แปลว่าสอบ5 วันติด8 9 10 11 12ก็ดีแล้วไงจะได้ปิดเทอมไปเลย
กูขอร้องเถอะ
No. So we're gonna keep this day because I knew it now. So you have the test on May 9, May 10, 11, and 12 and 15. So actually, pretty much you have like every single day for the final, like 8, 9, 10, 11, 12, 15. So it's better for you to get it done by 15 and then you can just go for vacation. But this one, I already submit that to พี่หมวย ว่าแบบว่า to afternoon นะก็ like keep afternoon แหละนะครับ เดี๋ยวไปเปลี่ยนเดี๋ยวคณะวิศวะเขาว่าเอาเขาอาจจะจัดตารางไว้แล้วจัดห้องไว้แล้ว เพราะฉะนั้นเราตามเขาไปเถอะนะครับ
แม่มาจำในห้องสอบเลย
อะไรมันต้องใช้เวลาจำกันว่าฟิสิกส์ขนาดนั้นเลยเหรอวะ
20ข้อมีแค่เลย
สุ่ม6ออก20อาจารย์
ก็จำวันจันทร์ตอนเช้าวันที่8ตอนเช้าไง
แล้วฟิสิกส์สอบเช้าสอบบ่ายฟิสิกส์สอบเช้าพ่อมึงตาย
Okay, today do you wanna learn integral now or you just wanna keep it for Wednesday because we have 40 minutes left but we are a little bit early than schedule because what I think is that we're gonna start the integral on Wednesday but we can start it now if you want to or you wanna wait for Wednesday so take a break first. So actually what we did here just we did the limit and continuity partial derivative the chain rule max and min problem already. So yeah we're gonna keep the schedule here so let's try to learn integral on Wednesday. So the time that we have left here so I'm gonna say that it's for you to study on differential equations and do the take home exam, okay? So we're gonna just start double integral on Wednesday and then we have 3 more class for double integrals. So next Monday and Wednesday we have no class. Also 17 we're gonna come back again on April 19 นะครับ April 19 so we have April 5 April 5th here and then April 19 the next one.